This is Nanoscape. I'm Seth Zimmerman.
And I'm Erin Spain.
On this show, we venture into the frontier of nanotechnology
With experts in the field who are turning the science of small into the next industrial revolution.
This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Today's guest is Todd Emrick, a professor of polymer science and engineering at the University of Massachusetts Amherst. His research is advancing nanotechnology through the design of entirely new polymers for medicine, electronics, and advanced materials.
Todd recently joined us here at the IIN for the Frontiers in Nanotechnology seminar series. So if you missed his talk, today's episode is your chance to go beyond the lecture and hear some of the stories behind the science. Todd, welcome to Nanoscape.
Thanks for having me.
Great to have you here.
It's good to see you again. So your seminar that you were just here for, it was titled Functional Polymer Chemistry at Nanoscale and Mesoscale Interfaces. And for people who couldn't attend, what was the big idea that you hoped everyone would walk away with?
Good question. You always hope people walk away with something, that's for sure. It's a lot of things rolled into one, really. That title is meant to bridge scales, and nanoscale structures on their own are wildly interesting for all sorts of reasons, some of which you mentioned. Then when you get into taking those nanoscale structures into larger scale materials, things that you can see and touch and feel and so on, that translates those properties to a larger scale. And so my lecture really tried to bridge those scales, starting with fundamental syntheses at the smallest scale, and then demonstrating how to put them together at larger scales.
So, and speaking of titles, the working title for this episode is The Soft Side of Nanotechnology. Does that feel right to you? What is, I guess, soft about the kind of nanotechnology you work on?
Yeah, that's a great title. You surprised me with that. That's a good one. Yeah, soft nano is a good concept. Soft materials, of course, are materials where you're often dealing with structures that are organic or polymeric in nature and composition. And we describe them as soft. Why are they soft? Because they're not made of metals or semiconductors or so on. They're made of the organics or the polymers side of that equation. So in fact, I'll give talks on what I refer to and many refer to as the soft-hard interface. So that interface when soft materials and metals, substrates, hard materials are in contact, what does that do to either of them electronically, mechanically, etc.? So yeah, the soft side of nano is an extraordinary field. To thinking a bit more as a polymer chemist, I don't have a degree in polymers. I worked on polymers as a graduate student, but not successfully. And it was really realizing as a faculty member here at UMass how polymer and nanoscience come together. And I think it's fair to say polymer molecules themselves are inherently nanoscale objects. And so when you think about nanomaterials or nanoparticulates, one can do things on a size scale with polymers that are very similar to that size scale that one can work on with gold nanoparticles or semiconductor quantum dot type structures. And so the soft side of nano is a big burgeoning field that's been extremely impactful.
Well, that word polymer, like for the average person, that might carry a different sort of meaning than the work that you're doing. They might be thinking of plastic bottles or grocery bags, but some of the work you're doing is improving solar cells, delivering medicines, creating new materials. Can you talk a little bit about that and how the polymer science that you're doing has evolved and is such an important part now of nanotechnology?
Polymers, of course, plastics are made of polymers. We have that whole thing out there. We've done quite a job in the world of populating the earth with polymers that are plastics. But polymers don't have to be plastics, and polymers can have all kinds of non-plastic properties that take them into different applications. So if you think about societal relevance and importance of polymers, you could start and stop with the semiconductor industry and how polymer lithography, photolithography, the ability to pattern chips at extremely small scales, how polymers were and are central to that process. The photolithographic process with versions of polystyrene make the semiconductor industry go. It's a good example where, on the one hand, polymers are making nanostructures. It's a top-down process, but it's still very nano in origin. And the soft-hard interface is essential. And so that's, an integration of polymers into a process that we're still developing the whole chip to nanoscale nodes to what will now now be an AI revolution. What is an AI revolution? Polymers are central there. So it's a good point you make.
Instead of relying on materials that already exist, you're designing new ones, and that's what you're really relying on. What tells you that the right material is not already out there and it's time to invent a new one? Is there a difference between discovering a useful polymer and designing one with intent from the start?
Part of it is simply what I do. And I grew up in graduate school as a synthetic organic chemist. Molecular design was what I learned. And so very often in projects in my group here, we'll start from the premise that we need a new material. And that's not always true. You can find really surprising and useful things with known structures. And yet, if we only rely on those, the discovery falls off. And so the molecular design, macromolecular design, that is extraordinarily important and is really core to what we'll do in my group. At the same time, that generates a new generation of students that are really good because they have that experience in design, novelty, coming up with structures that are new and novel. When they finish their thesis, they're ready to go off and do anything.
Yeah.
They could continue on in academics and go down those pathways, or they can get in, and very often do get into the industrial sector or the national laboratory sector. And because they've spent their thesis work creating, they're ready for everything. They're ready to use polymers that are known. They're ready to make new things. They're ready to bridge those interfaces. So anyway, it's a core that developing new polymers is core to what we do.
Can you just talk a little bit about your lab and what it kind of feels like to be there and be part of it?
I hope it feels good. Students generally look happy. I think it's a good vibe. We try to make it a good vibe. If you walk through my labs, they would look like organic chemistry labs. And it just so happens we're generally making polymers or we're making nanomaterials. We have benefited from, the work of, let me think of someone random, Chad Merkin, for example, of those particulate syntheses, the quantum dot syntheses from Paul Alivisatos and Munji Bawendi and Lou Bruce that were very influential in creating those new types of materials. So we'll have parts of our lab that work along those lines. And then to give a specific example, we spend a lot of time trying to come up with ways to stabilize nanostructures, as I presented in my lecture, to make them longer, brighter emitters, to make them more suitable for device layers in LEDs and solar cells, things of that nature. And that tends to require making polymers that have specific functionality, meaning some sort of elemental composition that literally likes the surface of a particle. And that often requires new syntheses because some of those materials just aren't out there. You just can't buy them. And so we end up going down a pathway of designing and synthesizing and then ultimately putting into practice new polymers for that soft-hard interface.
We've noticed that there's a sort of a theme in your work that some of the most exciting discoveries happen at interfaces. So can you talk about that? Why are the spaces where materials meet often where some of these bigger breakthroughs occur?
I think if you looked at my group's papers, interface is in the title of an inordinate number of them. It's not just these soft hard interfaces. There's a lot of fluid interfaces. We're very interested in and work hard on polymers that stabilize fluid droplets that arrange in certain ways at fluid interfaces, and how one can build structures in which emulsion droplets recognize one another, recognize all sorts of things in surfaces and materials and so on. So that's more a soft interface, and we work hard on that topic too. There's still a very large part of the research community that is fascinated by interfaces and that needs interfaces to work to make advances. So certainly that hits the electronic materials area, that hits medicine without question. It also hits fundamental understanding of what molecules or macromolecules are doing at interfaces. If just a coating of organic or polymer molecules on a surface, and if that coating has a thickness of some number of microns, that sounds thin, but the actual volume of material or the area of that material that's in contact with the substrate is very small relative to the bulk that's above it. So what kinds of spectroscopy can you use to probe that interface without interruption from the bulk? It's very hard. And yet those hard things are extremely important to do. So you see a lot of energy in the literature and in funding agencies for probing those kinds of interfaces.
A major focus of your seminar was on the polymers Zwitterion and what makes these materials different from more conventional polymers and why have they become so useful for so many different applications?
That's a great question. Zwitterions are getting very popular. We've been working on zwitterions for a long time, and yet we see the popularity growing, I think, which is good. We see work we've done being used by others, see a community growing. There's now a big zwitterion conference that's happening every other year. Of course, zwitterions come in a few shapes and sizes. The origin of these polymer zwitterions is really grounded in water and medicine. And so some of the class, like the phosphorylcholine zwitterion that I mentioned, this is one of the most or the most water-loving polymers known. And so these charges, of course, the zwitter of zwitterion means each little group on the chain has a positive charge and a negative charge, very close to one another. But it's not a typical counterion. The quote counterion doesn't float off into solution. It's referred to as an inner salt rather than a typical salt. And so water loves these structures, and water accumulates around these structures. So what does that mean? That means that if I take a polymer zwitterion that loves water and inject it into a living creature, an animal, ultimately a human, this is a polymer that is likely to be masked from the immune system, much more so than other types of molecules. So the body tolerates, right? We've done experiments where we inject very large amounts of poly-MPC into mice, and they're just happy as can be. They don't lose weight, they eat, which is important because when we attach drugs to those polymers, then we can shrink tumors, do those sorts of things. So that's one part of it. The other part of that people I think would find interesting is that when you find ways to attach those polymers to other polymers or to metals or other things, you again create a material that the body tolerates. And so if you look at some early work on this topic, especially from Japan, thinking of professors like Ishihara and Nakabayashi, they found ways to graft these polymers to the ball sockets of artificial hips. And so that's been a bedside to materials to medicine advance. And having those coatings on those artificial hips helps prevent inflammation, have a longer lasting joint, all those things that you want in an implanted material. Similar things in external use, contact lenses often have zwitterion components in them. Some coatings on stent devices have these structures. And so it's just a way to make a material more compatible with the body. And zwitterions do that very well.
One application that you've highlighted involves improving the stability of pavskite nanocrystals for next generation electronic materials. So tell me, what problem are you trying to solve here, and what becomes possible if you are able to make these materials more stable?
Yeah, this is a good example of the evolution of light-emitting nanomaterials. And what started in this field in the quantum dot area, the cadmium selenide nanocrystals, things of that nature, and that are still progressing, has transitioned to some degree into these perovskite structures. They're really interesting. Bulk perovskites, non-nano perovskites, have revitalized or advanced, certainly, the solar cell field. The nanoscale perovskites that we've been working on are simply bright emitters. And very interestingly, as one changes the elemental composition of those perovskite nanocrystals, one sweeps through the visible spectrum of light, and you can build an array of, in the solution state or solid state, of colors, and then mix and match colors to get the sort of displays that one's interested in. There's a big problem with these perovskite nanocrystals, and that's related to their instability with respect to polar solvents, with respect to heat, with respect to some other features that are typical of device manufacturing. And so coming up with ways to protect the nanoscale structure with what we call ligands, so surface-bound ligands, is really very important. Amazingly, zwitterions do this, right? So, if you look at our history of work over the years, one thing that we found that I still enjoy talking about it so much because it was a real surprise to us. And it's a surprise that you could say, has legs. We've been working on it for well over a decade now. And that is these interact electronically with conductors and semiconductor structures in very productive ways. And for perovskite nanocrystals, they apparently bind to those surfaces, those perovskite nanocrystal surfaces, very effectively. That aids stability, and that improves brightness, and that improves manufacturing stability. So this has been a really productive line of research, and we just want to keep advancing it as far as we can.
Your research really does span medicine, electronics, and advanced materials. And to a lot of people, that sounds like very different worlds. Your lab really kind of swims between them pretty easily. What does polymer chemistry give researchers that make those connections possible? Is there like one kind of through line, one question that follows you across all those fields?
Some years ago, we wrote a paper, and this was an enjoyable paper to write. It was with my colleague Tom Russell and my University of Pittsburgh colleague Anna Balas. We wrote a paper called Polymers and Nanoparticles, where two small worlds meet.
Oh,
Right?
sounds like
Yeah,
a
right.
children's book. I like it.
Yeah.
It sounds, I hope it reads a little bit better,
Right,
but
right.
nonetheless, I mean, that was our first description of those worlds coming together. And really fascinating things. Nanoparticles are solid objects and they have a certain well defined size and rigidity and so on. And polymers are soft structures and they're made of chains. And so, one of just the many intricacies about how those worlds connect are the ways that polymer chains wrap around the surface of particles. And in fact, if you're a polymer chain, stretching and wrapping isn't actually something you want to do. There's a entropic penalty associated with that, right? They'd rather be coiled up in less stretched structures. And so just thinking about how those structures mix when you get to very basic questions of, can I disperse particles within a polymer matrix to make the properties of both better? Sounds like a pretty simple endeavor. It turns out to be really very complex on multiple energetic levels. So, but your question was, how do students navigate those different areas? And I think one key is, at least in my labs, is that when you become proficient at new syntheses, right, identifying targets, making small and macromolecules for those targets, some of those targets then become reachable. If you go through my labs, you see a very classic synthetic component to that. You see all the characterization tools that we need, or if we don't have them, we find them on other places on campus. And then you see membrane characterization areas and cell culture work that we can do in our labs and that whole range of things. For example, at this moment, we have a project where we're working on carbon materials and integrating dopants into them, nitrogen and boron in particular, and then taking them right into the cell culture room and looking at the response of live cells on those new types of surfaces. So you get immediate feedback in terms of structure property relation.
As industry, clinicians, are people coming to you with their problems? Or are you out there kind of understanding what the problems are and coming up with solutions? How does that work?
It's really both. It's a two-way street for sure. Science as a contact sport is a important way to view what we do, not working in isolation with your head in the sand for sure. So yes, companies come to us and, in part, companies come here because we're polymer and that polymer industry is robust and there's lots of interest in advances, but we have to go there too. So for example, the talks that I give, there's always a potential for industrial participation in the audience. And so that's a way to meet people that are interested in problems that you're working on. I, over the years, have been to many conferences, given numerous talks on flame retardant polymers. And that's an area where industry is really in need of new solutions, just like we're in need of new solutions in polymer adjacent or polymer areas and in microplastics and in PFAS and all of those topics where industry is in that tough position of materials performance versus regulation and where are they going to go and what are you going to do? So on our side of the equation, working with companies along those lines, and being able to take a chance on new materials or tweaking known conventional materials just enough to change properties is an important thing.
When you do get called in, and because these two materials aren't talking to each other, what is, I guess, the most unreasonable thing that the researchers expect polymers to fix in those situations?
I think cost is the most unreasonable thing. There's a lot that one can do and demonstrate, and that demonstration, in my opinion, is the critical point after one can iterate and scale, or at least have a chance. But when we want it to be better and less expensive at the same time on the first try, that's almost a showstopper. And yet, I think that if you're sitting in a certain management position in a company and you're at a whiteboard and you think, let's challenge them with this, make it better and cheaper at the same time. Okay, And sometimes we engage in those projects and we try. And what usually comes out of that is a lot of new fundamental understanding, and people have to take it from there.
Hmm.
Right.
Mhm.
And really, again, in my view, that's the role of the industrial sector. And as much as, of course, we can and do have ideas, patent ideas, license patents, could start companies, right? Things of that nature. In the end, there's an industrial workforce out there, and that's what they do very well.
For sort of the everyday person who might be listening to this, what would you like people to know about polymer science?
You know what's interesting about polymer science? If you just look at my department and my colleagues, almost none of us have degrees in polymers. We didn't grow up in a polymer education. We're chemists, or we're engineers, or we're physicists, or theoreticians. And that's really wild. And then all of these fundamental disciplines come together to work on a soft materials problem. There's enormous contributions one can make to that. So polymers in soft matter physics, polymers in functional polymer chemistry, polymers in engineering and rheology, and just the ways you can make and break polymers is really interesting. Because I work in this place, I've learned more polymer mechanics and engineering than I probably would have if I had gone to a more traditional chemistry department or something of that nature. So I'll never pretend to be an expert engineer, an expert
Yeah.
physicist. It's impossible. However, you get an instinct for those fields and how they intersect with chemistry, and that turns out to be really productive. For young people thinking about entering a field, we have this little thing where, polymers as plastics are taking a certain beating in the world, and yet that's just such a fraction of the power of polymer science as a discipline, as a field, and as a field that intersects essentially with everything. We haven't even talked about natural polymers and proteins and DNA and RNA and that whole bit, but even in the synthetic polymer field, it's the intersection with nearly everything is wildly interesting. Electronic materials, without question, high performance materials. So, all of the materials that one needs in vehicles, in space. Imagine you have this opportunity not to devalue the importance of metals and wood, ceramics, right? But you have this wildly interesting type of material that has, at the same time, it can be very strong and weigh very little. And so when you think about the benefits of that, just the fundamental benefits of that, it's really compelling. Protective materials in military applications, just protecting soldiers, protecting people, extremely important. And the types of materials one needs in athletics. Polymer science that goes into making a better football helmet to prevent concussions. There's no end of these. I mean, we could talk about fabrics, we could talk about clothing, and then single-use plastics. Of course, that's just another hot area that creates problems. On the other hand, without them, imagine a hospital that didn't have access to those. It would be an entirely different scene. So we need all these things. Society needs them. We need to make them better. We need to make them more sustainable. We need to make them as reusable as possible. But that's going to take time, and it's going to take resources, and it's going to take giving academic settings and companies the time and resources that they need to improve these components.
When we invite you back to Nanoscape in 10 years, what breakthrough in polymer chemistry or nanotech do you think we'll be talking about or hope we'll be talking about?
The discoveries that happen when you're looking for one thing and the other thing happens are pretty amazing. We've been involved in some really difficult projects that are first principles fundamentally hard and are still in need of real serious development. We were involved in a project associated with atmospheric water extraction. And the core idea was, this happened to be a DoD supported project. The core idea was that one could take a water extracting device into the desert with 12% relative humidity and it would extract water and you could drink it, right?
Wow.
And that's asking a lot. And so there were teams involved and we were the team working on the polymer component of that. And from that effort, we came up with all sorts of ways to make highly water absorbing foams that one could pull water out of the atmosphere with, not quite at the level where you could drink it, okay? But progress. It's just one example of many where we're not quite there yet. So much more work to do. And yet at the same time, that particular project gave us an expertise in the area of biofoams, right? Making foams from nature's materials, right? Nature's polymeric materials. And in fact, we just finished a piece of work where we took took that in a different direction, and we're able to make foams that have the same mechanical properties as styrofoam, and they're made from waste sawdust. Literally, my student went to a local farm, asked for their waste sawdust, brought it back to the lab, and made a a
Wow.
styrofoam replacement with it.
Oh, that's
So
incredible.
yeah, in fact, we just published that a couple months ago. And so, I mean, are these specific examples of the big breakthroughs waiting to I think the big breakthroughs come when you start to be able to use materials in ways you just couldn't do it before. And we've learned a lot about the scope and limitations of what any particular polymer or material can do. And then the question becomes, can I maximize a material's properties by making hybrid structures, right? Polymer, metal, semiconductor, biological component, right? Those sorts of things. And that becomes, for every component you add, it becomes more complex. But it's those kinds of hybrid materials that, gaining that understanding will open up new things.
Thank you so much, Todd, for coming on the show, talking about your career in your lab and all the work happening in polymer science. I think this will be very fascinating for our audience.
It's my pleasure. Thank you.
Thanks so much for listening. This podcast is brought to you by the International Institute for Nanotechnology at Northwestern University. Be sure to follow this show on Apple Podcasts or wherever you listen to podcasts, and be sure to give us a 5-star review.
For more information about IIN, go to our website, iinano.org/podcast.